Good evening. It's my great pleasure to introduce Doina Precup, who is a associate professor at McGill University in Montreal, Canada, and she's a well-known and well-known researcher in the field of theoretical reinforcement learning. So I'm very happy that you have decided to join our school. Let's start.
Okay, thank you for the introduction. So I will talk about temporal abstraction and reinforcement learning, and I would be happy to entertain questions from the audience as well, if that's okay with the organizers. What I'm going to talk about is actually work that's been going on for almost 20 years now, some of it in collaboration with Rich Sutton, Satinder Singh, and my graduate students, more recently, Pierre-Luc Bacon and Jean Hart. What I want to do basically is to give you an overview of temporal abstraction and reinforcement learning, and also discuss some very recent work that we have just published at AAAI and a few other workshops, just to give you a flavor of the things that we are thinking of right now. So what's temporal abstraction? Well, if you think of sort of everyday activities, like say cooking dinner, typically these activities involve...
Can you share your slides, please?
I think I am. Hold on.
Actually, you can see what we see on our screen.
Okay, let me just try to share again the slides. Do you see my slides now?
Yes.
Yay, excellent. Do you still see them now?
No.
Okay, so I can't, got it. I can't enter full screen, otherwise it doesn't work anymore. That's the problem.
Just show them in the...
I'll just show them like regular view.
Yeah. Yeah, we see them.
That's perfect. Okay. So temporal abstraction basically refers to the fact that sort of complex activities typically have some high-level steps and then some low-level steps in terms of the time scale of these. So, you know, if you're thinking of how to cook dinner, you might figure out a recipe and then make a list and so on. And you know, when you're actually cooking, you might do some activities that maybe take a medium amount of time steps, like, you know, getting a pot and putting the ingredients in and so forth. And then there's some low-level motor movements, like your arm might be moving, your wrist might be moving, and so on. And so all of these things have to be integrated. And actions and thinking at all of these levels of temporal abstraction have to be integrated into one system. In classical AI, this has been done through the framework of macro actions and hierarchical planning. In robotics, this is done using controllers. And in reinforcement learning, there have been different formalizations of temporal abstraction that have started, you know, basically at the end of the 90s. I will specifically focus on the framework of options, which I developed in collaboration with Rich Sutton and Satinder Singh. So I will try to explain a little bit the specifics of this framework and then talk about sort of recent results of this framework. So we're going to assume sort of a standard reinforcement learning framework where we have an environment that is a Markov decision process. A Markov decision process is specified by a set of states, a set of actions, a reward function R that essentially tells us how much immediate reward is received for every state and action, and a transition probability matrix that tells us that probability of the next state conditioned on the current state in action. And I'm going to be using the discounted framework. So there is a discount factor gamma that is typically chosen less than 1 and tells you how much sort of future rewards are valued compared to immediate rewards. So now we're going to introduce options in this Markov decision process in order to represent courses of action that might take a variable amount of time to complete. And so an option, I'm going to denote it by the letter omega, has 3 components. There's going to be an initiation set of states, I omega, so that's a subset of the state space. Sometimes people also call this a precondition. Then there is a policy, pi omega. So a policy specifies how primitive actions are chosen while the option is executed. And so it's just like a regular reinforcement learning policy, has a conditional probability of actions conditioned on the state. Different options are now going to have different policies. And then there is a termination condition, beta omega. Beta omega maps states into 0, 1, and it essentially specifies the probability of terminating the option when you enter a particular state. So for example, if you imagine a cartoon robot navigation task, you might have a navigation option that essentially consists of going forward. And the initiation set is, well, you can go forward when there's nothing in front of you. So I omega would be the set of states where there is not an obstacle too close. The policy might be just execute a forward motion. And the termination condition is if you get too close to another object, then the termination condition gets triggered. So there's this framework was described in my PhD thesis, also in a journal paper that we published in 1999, that gives all the details of this representation. What I want to emphasize here is that one can actually think of options as a form of a behavioral program. And from this point of view, typically options are executed in what we call and return execution. So you think of an option as a little subroutine that gets called by a policy over options. When it gets called, then the option executes. So you push the identity of the option on an execution stack. The program looks at certain variables and executes primitive actions. So you can think of these variables as the state and the actions as a form of instructions until you reach a termination condition. And it's actually okay for the option to have internally some other things that it keeps track of. For example, I might want to keep track of the duration since the option has started executing, or perhaps how often a certain feature occurs while the option is executing. And one can make termination conditions based on these as well. So for example, we can have an option that times out after a certain number of steps have been spent. And in fact, options can also call other options. So one can have multiple levels of these built on top of each other. So essentially, options are like little subroutines in a programming language that you call. They choose actions while they're executing, and then they return. Now, this is the typical call and return execution. Much of the existing work and the things that I'm going to talk about use this execution model because it's quite straightforward. But we can also allow options to be interrupted. So this is, again, sort of similar to interruption in concurrent systems. And essentially, we are going to allow interruption when an option is executed and we notice that something better has become available. And the other thing that I'm going to say is that the option identity is actually also in itself a form of memory, but it's not a memory of the past, of where the agent has been. It's actually sort of remembering what is the agent trying to do. And so, for example, if I have a navigation option, this option might be to navigate to a specific target. And so that's the sub-goal of the agent. And the identity of the option essentially is giving you that sub-goal for the agent. So now the other thing that I will say is that options can have models. And in reinforcement learning, we're used to models basically being an expected reward and a transition probability to different states. Now, option models are basically an expected reward that will be received while the option is executing, and a transition model to a next state, with a little caveat. This transition model is not anymore a probability distribution, but it actually also reflects the time that the option will take. And this time is going to be incorporated using the discount factor. So basically, notation is P omega of S prime given S. This will be a conditional probability distribution of S prime, but discounted by the duration, by gamma to the power the duration that it takes the option to execute. And so basically, P, this transition model, specifies both where the agent will end up at the end of the option, as well as when the end is going to happen, when the termination will happen. So you can think of these models essentially as predictions about the future conditioned on the option being executed. And in terms of, thinking again of the analogy to programming languages, basically option models provide semantics for the execution of the options. So you can think of these models being essentially a form of post-condition of what would happen when the option terminates. Well, some reward will be received, there will be a follow-up state, and some duration would have elapsed. And so the models capture these. And the interesting thing is that these models are actually compositional. And so on the slide, we have two simple rules for sequencing options, for example. So if I think of an option omega-1 followed by another option omega-2, if we want to determine the transition model for these options, well, we consider just the successive application of the transition models. And so this is just multiplying the two transition matrices that correspond to the two options. And similarly, if we have a reward model and we're thinking of the reward for omega-1 followed by omega-2, well, we take the reward for omega-1, then we consider what transition does omega-1 make, that's captured by P omega-1, and then from then on, omega-2 executes, and that will give us reward omega-2. So we have these kinds of compositionality conditions, and the interesting thing about this is that they give us conditions to allow Bellman equations to hold. And actually, that's quite nice. We have here sort of a cartoon of what options do a Markov decision process. And the nice thing about it is that a Markov decision process in which we have options basically becomes a semi-Markov decision process. Now, just to sort of recap, since semi-Markov processes are not used quite as often as Markov decision processes, a Markov decision process has a sequence of states and actions that happens with a discrete and fixed time scale. So time ticks, you're in this state that represented by a little dot, you take some action, then time ticks again, you take another action, and so on. So all the actions have fixed duration, and that duration is essentially one time step. In a semi-Markov decision process, there is a state, then an action gets chosen, and that action has a duration that may be stochastic. At the end of that action, you have a choice again. And so the evolution of the system is shown by this trajectory with the empty circles. And you can see that the different transitions actually take different amounts of time. Now, what happens when we have options in a Markov decision process is that we essentially have a semi-Markov process at the level of choices over options. So an option initiates, takes some amount of time, then it terminates, and you have another choice. But at the same time, while the option executes, it's choosing primitive actions which are inside the MDP. So we have a semi-Markov process and the Markov process both coexisting at the same time. And the nice thing about this is that we can import all planning and learning algorithms from classical MDPs and reinforcement learning into the option framework. But using the options actually gives us a speed improvement. And so to illustrate this point, we can look at this navigation problem. This is a very simple problem. You have a grid world navigation task. You have a little agent that can go up, down, left, or right. There is a goal state that's represented by the green circle. And so you get a reward of 1 when you enter the goal state and the task terminates. And if we were to use primitive actions in order to do planning here, we can use your favorite Markov decision process planning algorithm, value iteration or policy iteration. And essentially, a couple of iterations are shown in these pictures. Of course, there's no rewards except when you go to the goal. And so planning iterations, essentially, we will propagate these rewards slowly from the goal backwards. And so in the first step, the 2 states adjacent to the goal get some value. In the next step, the states that are 2 steps away from the goal get some values, and so on. So this process, of course, it is going to converge to the right values everywhere. However, it's going to be quite slow at filling up the space. Now, suppose that somebody gave us options that can navigate to the hallways in this environment. Okay, so these are sort of room-to-room options represented by these arrows. And suppose that we actually have models for these options that tell us what's the reward obtained and what's the transition probability when we do these. Well, now we have an environment where we have a goal, and from the goal, we can actually propagate backwards these values to a whole room at a time. And this is sort of the magic of the option models, which give us these estimates from many different states. And so a step in an option planning algorithm is a whole option. It's a temporally extended step. And so this is what you see here. Basically, in 2 iterations, all of the states in the environment have some value. These values are not perfect, but they allow us to navigate actually to the goal successfully from pretty much anywhere in the environment. So that's actually quite a nice thing. And similar speed-ups have been observed in many different tasks, inventory management tasks, robotic tasks, and so on. Now, this is another little illustration which shows you what happens even if we have options that are not sort of perfect, but that are chosen at random. And so the basic idea here, this is work that we published fairly recently in Journal of AI Research. And the idea here was that if we had a navigation task, we were going to pick at random a bunch of landmarks in this environment and then have a simple, short planning procedure so that a landmark can be reached from a limited area around it. And so in the second figure here, you see these little ellipses. Basically, the center of each ellipse is a landmark. And from inside the ellipse, you know how to reach it. And this can be done using a deterministic approximation of the environment, for example. It's all sort of very simple planning. So now we choose a set of landmarks at random, and we can navigate essentially by leapfrogging from landmark to landmark. And this is an algorithm that we call LAVI, Landmark Approximate Value Iteration. At the same time, we could be using primitive actions. In this case, we have quite a large environment. We have to discretize the action space. So that's primitive fitted value iteration. And so you can see in the PFVI figure that this trajectory still stays all curled up in one corner because primitive actions simply don't take you far enough. Whereas when you're using landmarks and options, you can actually sort of find a trajectory. It's not a perfect trajectory. It's not the shortest path, but you can find the trajectory very quickly from the start state to the goal state. And then essentially you're sticking to the goal state by sort of jumping around there. And the solution is obtained much faster in terms of the number of iterations and so on. Are there any questions so far by any chance?
Not yet, thank you.
Okay. So then we're going to talk a little bit more about sort of what's inside a model of an option. So here we have a little bit the anatomy of a reward model for an option. For a primitive action, the reward is just the expected reward that's conditioned on doing a particular action in a particular state. Now, for the option model, we have the expected reward that we obtain while the option is executing. And the interesting thing is that this model is basically a value function, and there's a Markov property inside of the model, which comes from the fact that the environment that we live in is a Markov decision process. And in fact, one can write out a little Bellman equation for the model, which is written out over here. So we can decompose the reward coming from state S into the reward for the very first step, RSA, and then the reward that's obtained from then on, from state S prime on. And this is also using, of course, the probability of continuing from the following state onwards, which is 1 minus beta of omega. So this is very nice because it allows us now to use reinforcement learning methods to learn the models of the options. And in fact, we have very similar equations for the transition model as well. And we can take these into a learning algorithm, which is called intra-option learning, both to learn the models as well as to learn about the option values. And here, there is, on the slide, there's an example of an intra-option learning algorithm that is trying to estimate what will be the value of executing some option omega at state S. Now, the interesting thing is that we can actually estimate this from any kind of trajectories, so long as these trajectories are actually consistent with what option omega would do. And the basic idea of this backup or update is that we look at the first reward that we get after action A, and then we can mesh together either the value of continuing with omega, this is the sort of term gamma times 1 minus beta omega of S prime times Q omega S prime omega. So this is saying, what if I continued with omega in the next state? What would happen? If we terminated according to omega, then we would do the best possible thing afterwards. This is the max term here. And so now we can make an update essentially with these two possibilities. This is using an expectation at the next state, but of course the next state is just a sample. And so this is an algorithm that can also be generalized when you use function approximation, whether it's deep nets or something else, by using importance sampling. I'm not really going to talk about that, but there are several papers that have shown how to do this type of learning with importance sampling. These kinds of updates are also called off-policy learning because you are updating potentially the values of many different options that are all consistent with the observed behavior, and this is done all in parallel. Now, this is all good. I hope I convinced you that options are nice, and there's some interesting learning algorithms that allow you to figure out how to use options if a set is given to you. The big open problem and the frontier in the research in this area for a long time has been option discovery. So what we mean by this is that we would like to find a way to create options that are appropriate for the task. In other words, if we have a complicated problem, we would like to break it up into chunks that take place over multiple time scales, and these chunks should somehow be good, either in the sense that they help the agent plan faster, or they help the agent learn faster. Now, a lot of the time, the way that this has been tackled is by thinking of sub-goals or secondary reward structure. So if in the navigation task, I could put extra rewards for the agent in the doorways, then the agent would be drawn to the doorways and would learn those sub-policies, and then we could cache them in as options. If such a secondary reward structure is given, then we can learn the option policy very easily. It is essentially the result of a smaller planning or learning problem. And that's all very straightforward, because essentially we have a little MDP that we can solve and we can cache in the solution. The interesting thing from a research point of view is how to find a good set of sub-goals or options. And this is essentially a representation discovery problem that people have been thinking about for a very long time. There have been several attempts for doing this. For example, based on detecting special states, like these doors are kind of bottleneck states where many trajectories get funneled through. This is all kind of interesting, but it doesn't quite help us in the sense that these methods tend to be very slow and certainly require more effort in order to come up with a set of options than would be required just to solve the problem from scratch. So what we have been focusing on in the last year or so is to make an approach where we can specifically state an optimization objective for a set of options and then solve this objective to find a good set of options. We would like this to handle both discrete and continuous states and actions and work sort of very well with function approximation, like neural nets. And we would like the learning of the options to be continual. So what I mean by this is that oftentimes people have thought of this problem essentially as two stages. First, learning some sub-goals or reward structure, and then learning policies over this. And the first step has often been tackled through graph-based methods, which have a very combinatorial flavor, and hence they're very expensive. So we would instead like options to kind of gradually improve over time. And the other sort of important goal, is that we want these options to provide improvement even within one task, or at least not to slow down the learning, even if we have just one task. And so all of these desiderata have suggested to us that the way to go would be to get inspiration from a classical reinforcement learning architecture called the actor-critic architecture, which is pictured here. So in actor-critic, we have a separate representation of a value function and of a policy. When the agent interacts with the environment, both the state and the reward are given to the value function, and the value function trains using usual TD-style algorithms. But also, there's a gradient signal that gets computed based on this value function that's given to the policy. So the policy is parameterized separately, and this gradient essentially tells the policy how to modify its parameters. And there's a very clear optimization objective, which is just to optimize return, the usual discounted return reinforcement learning objective. And the interesting thing is that this is continual learning. On every transition, we get some information, we update the value function and the policy in parallel, and it also handles both discrete and continuous states and actions. So what we worked on, and actually my student is presenting today at AAA 2017, is a similar type of architecture, which we call the option-critic architecture. So like in actor-critic, we're going to have a critic and an actor. The critic is now going to have an action value function over options, as well as some information, some helper functions that I'm going to show you in a minute that are essentially going to help keep track of gradients that are needed for the options. Now, the policies and termination conditions of the options all live inside the actor, together also with the behavior policy over options. And so we are going to have a parameterization for internal policies and termination conditions. The policy over options may be computed through a similar process or not. It could be computed, for example, via planning if we want. And the little switch here essentially says when an option is executing, we select it, it chooses the actions. So its policy and termination condition sort of control the choice of primitive actions. Primitive actions go to the environment, and the data gets used to provide gradients on how to improve the policy. And like in the case of Actor-Critic, this is based on optimizing, simply optimizing the discounted return objective. Now we're going to look a little bit at how these helper functions are constructed. Just to give you a bit of sense of the math, and the details are in the paper, which is called the Option-critic architecture, so you should feel free to, to look there. So the formulation is that we have a policy pi omega over options, and we're going to decompose its value into a set of value estimates QU S omega A, and these are now the values of the different primitive actions executing in the context of being in state S and currently having picked option omega. So you can think of this as essentially omega becoming part of the current state. Now, what are these action values like? Well, they can be computed using immediate reward, plus when we go to the next state, we have the value for arriving in that state using omega, and we denote this by big U. So big U of omega S prime is the value of arriving in S prime using option omega. And we can also spell this out a little bit in terms of from what happens from then on. Well, either we continue with omega or we terminate according to its termination condition. And these are the two terms in the equation that defines big U. So now we can parameterize internal policies by theta, S pi omega theta. We can parameterize termination conditions as well by some parameter vector nu. You know, think of these as being deep nets or whatever other function approximation device you want. And notice also that these parameters, in fact, could be shared over the options. And in our experiments, we sometimes do share these parameters over the different options. So now what we are going to do is take gradients of our optimization objective with respect to these parameters, theta and nu, and use these to improve the option. So the main theoretical result that we have is these gradient updates for optimizing expected return. And the details of these gradient derivations are in the paper, but it's actually interesting to consider what they do. So first of all, we can look at the gradient with respect to the internal policy parameters. And this basically, this formula here for the gradient says, if some primitive action has a better value, it should be taken more often inside the option. And so the gradient term is going to push the probability of that primitive action up, and the other primitive actions will be, of course, pushed down. The termination function has also a gradient, and its gradient is based on the advantage function. The advantage function says how much better is an option compared to the average value of the policy over options that we currently have. And this formula essentially says if an option has an advantage over the policy over options, you should continue doing it. And if an option has a negative advantage, that means it's better than average, you should terminate it with higher probability. So here, betas are going to be probabilities between 0 and 1. And essentially, we are pushing these probabilities up or down based on the advantage of the current option. Options that have a big advantage are going to be lengthened, and options that have a negative advantage are going to be shrunk. So that's the basic idea. Now I'm going to show you some results of how this works. And the first results are basically an illustration that we did in the rooms domain that I showed you before. And here we have the SARSA algorithm to learn value functions. And what we do is we set a goal in one of the rooms. We learn a policy for reaching that goal, either using primitives or using the Option-critic framework. And we tried here 4 options or 8 options, but of course we don't have to provide any extra information to the framework in order to do the learning. Then after 1,000 episodes, we move the goal state and we look at how fast the 2 algorithms are able to recover from this move. And so what you see here is, first of all, learning with the options is really not slower in the first task than learning with just primitive actions. And this is really great news for us because this was one of the impediments to using option construction in previous work, that it slowed down learning. And here we observe a very negligible effect in terms of that. Essentially, the speed of learning is the same. The other thing that we observe is that after the goal gets moved, after this big spike in the middle, the options actually are able to find the new goal much faster compared to the primitive action representations, either using SARSA or Option-critic. And this is, again, something that we were really hoping to see because options are understood to allow us to transfer knowledge better between different problems. And so here we see an example of this knowledge transfer in action. Now, we also did this in the Atari domain. Hopefully you're familiar with this. This is a set of problems that was introduced by DeepMind and has been used as a benchmark in the community for the last 3 years or so, quite extensively. It consists of 50 different Atari games. And so here we're using the Atari simulator. I'm showing you results here on 4 Atari games: Asterisk, Pac-Man, Sequest, and Zaxxon. And on top, we have the architecture that we're using for function approximation. So we're going to use a DQN-style algorithm to learn the value function over options. But the architecture essentially has a bunch of convolutional layers. And then out of those, we obtain a set of features. And we're going to use the set of features simultaneously to represent the policy over options, the termination conditions of the different options, and the internal policies. And here the termination functions are modeled as sigmoids, and the other sort of parametrizations are essentially Boltzmann policies. And what we see in the results, it's a little bit hard to see the DQN lines. I think I'm going to give you better graphs if you want to post the slides afterwards. So that actually the options in all of these cases either exceed or basically match DQN performance. So for example, in this task here, there's a sort of faint horizontal line here, which is the DQN performance. And we see the options exceeding this with the same amount of training. And similarly in the other tasks. So again, this is a case where we have one problem, we provide no extra information, and we have this algorithm which is able to beat DQN performance. We have actually more recent experiments now using the A3C architecture proposed by me and colleagues. And again, we see a very similar result that using Option-critic with A3C provides an improvement over plain A3C. And this here is showing some sort of qualitative results, looking at whether the options that are learned are actually intuitive. So in the room's environment, we see here in light color the places where terminations are more likely. This is for the different options. And what you can see is that basically the probability of termination increases around hallways. It's interesting that this is falling out of the representation without us having to put that prior knowledge in. And on the bottom of the slide, you see Sequest. And here we have 2 options that are sort of represented by white and black stripes on the top line. And what you can see, first of all, is that the system is switching between these 2 different options, and that each option actually is taken for quite some period of time. So there is good sort of temporal coherence in these options. The other interesting thing, sort of zooming in on this little red box here, is that we have essentially one option, the white option, which takes the submarine up to the surface. And then the other option essentially takes the submarine down. And this is a very consistent result that's occurred over multiple runs, is that these options specialize to take these two different behaviors. So this has been a very sort of positive results for us, and we've enjoyed having this this option-critic architecture now giving us a sort of graceful way to construct options. But one effect that we did notice is that the options that get constructed actually shrink over time. So for example, in Sequest, we have these options that go up to the surface and then down. But if you let the system learn for a long time, the options are going to shrink and essentially dissolve into primitive actions. And this is actually expected because our objective, our optimization objective, is simply to have sort of a good expected return. And we know that primitive actions allow us to achieve optimal return. And so from that point of view, we actually need to think a little bit about how to encourage longer options, which increase the speed of learning and planning. And in order to, actually I'm going to skip this. In order to understand how to do this, we're going to look a little bit at the anatomy of the value function over options. And there's nothing really fancy on this slide, just to show you can manipulate these equations a little bit. And by manipulating these equations, we actually obtain an equation for what I will call a flattened policy that marginalizes over options. So essentially, if you have a fixed policy over options, you can kind of flatten that out and obtain a reward and the transition matrix for what would be the marginal probability over primitive actions if we take the options completely out of the equation. And we can rewrite policy evaluation step using this new notation. So here we have the matrix H for the transition matrix. P sigma is giving us the marginal transition probability with the flattened policy. And when we write this all out, we obtain a linear system of equations. And the interesting thing is that this linear system of equations actually corresponds to an old sort of linear algebra concept that was presented by people back in the 50s called a matrix splitting. And one way to think of a matrix splitting is that it's a form of preconditioner. It's a form of taking a matrix and transforming it to make a system that is more easily solvable. And so, we can do this in the context of a linear system. Here, if we do policy evaluation, of course, we do have a linear system. And a preconditioner basically says that we can write the matrix A sometimes as a difference between two matrices M and N. And if M is non-singular, then M and N form a splitting of this matrix, and we can approximate the solution of the system by an iteration. And this matrix M now, we can sort of toy around with it in order to make these iterations faster. So we can, for example, design it in such a way as to manipulate its spectral radius, and that would give us sort of good productive iterations. Now, the literature in terms of how to obtain good preconditioners is actually kind of open. So in general, there aren't good ways of doing it. But what I would like to point out here is that essentially what we're doing when we're constructing options is we're defining a specific matrix splitting. And for options that have the same sort of internal policy, having longer duration actually leads to better spectral radius in this matrix splitting. And so we would expect updates to take fewer iterations. And so that's one way to sort of formalize this intuition that having long options would be nice. So now what is remaining is to actually tell you a little bit about how we might construct a good preconditioner. This is actually very much work in progress. So these are some initial ideas that we also presented in a NIPS workshop last year and we're working on currently. And the proposal is to use deliberation costs. So deliberation costs are coming from a framework of thinking that is called bounded rationality. And the idea is that agents have limited computational resources, and thinking essentially consumes these computational resources. And so we need to do it in a sparing fashion. And so here specifically, we're going to assume that executing a policy is cheap, but deciding what to do between the different options is actually what's expensive, because we need to evaluate different value functions to do this. And if we're doing planning, maybe we need to consider many different states and so on. This is actually an intuition which is very much in line with what people think in animal learning. In animal learning, energy consumption is an issue because the brain has sort of eats up a lot of energy. But also, if an animal is sitting around thinking too much, then it may miss some opportunities. So, you know, the tiger is sitting there thinking and the prey just runs in front of it, then the tiger might completely miss the prey. So there's a missed opportunity cost to thinking for too long. And so the proposal that we're working with at the moment is that we're going to have a cost imposed for deliberating how to choose an option in a state. This is called CS omega. And if we're using call and return execution, it's actually pretty straightforward to show that there is a value function that expresses the total deliberation cost. It has a corresponding Bellman equation. And this now gives us a new objective that we could solve, which is to maximize reward while at the same time spending reasonable effort. So this is the objective on the bottom here, which says the current reward is Q omega, and then we have some costs associated with deliberation. These are given by QC, and there is a Lagrange multiplier here, Xi, that controls the trade-off between how much we care about getting good value and how much we care about computational effort. And so we can plug in, the nice thing about Option-critic is that it will work with any kind of reward objective. And so we can simply plug this new objective in and run the algorithm and optimize it. This is just an example of what this does in the 4 rooms. And so in the first graph here, you have a deliberation trade-off parameter on the x-axis. You can see that as you if you have a very high penalty for deliberation, you actually obtain a policy that is always choosing just one option. Whereas if the penalty for deliberation is lower, you might in fact favor primitive actions, because then actually obtaining the best reward possible becomes important. And on the rightmost graph, this plots the for the different values of this parameter, the failure rate compared to the number of steps taken. And you can see that basically the options are all bunched together lower than the primitive actions. So when we use, and sort of part of the message here is that not only is the number of iterations of planning smaller when using a higher deliberation cost, but also we have better transfer properties in different tasks. And in fact, we are currently sort of working on analyzing these effects using the matrix splitting framework that I just showed you. So just to conclude, Option-critic is a nice, I think, way of doing continual option construction. I hope some of you will look at this paper and perhaps look also, we have a GitHub repository with code, and try to play around with it some more. We're looking for sort of people to try this out on different problems. Matrix splitting is an old but very interesting analysis tool. This problem of designing good deliberation cost and including deliberation cost is still very much open. The other thing that we're currently working on quite a bit is this sort of bullet over here of how to incorporate initiation sets. Our current framework mainly focuses on options that initiate at every state, but we would like to go back to the framework where preconditions are allowed. And so that's an open question right now. As is sort of getting more empirical intuition onto how these methods actually work. So I will stop here, and I would be happy to take questions regarding any parts of the talk or any reinforcement learning notions in general.
Doina, thank you a lot for your great talk. And we have questions here, but before we will start with the questions, can you hear us?
Yes.
You should know that we are not doing usual science school or bootcamp for deep reinforcement learning. It is combined with a hackathon, with a competition on Atari games. So, awesome. So the teams during 1 week should solve one Atari game, and this week is especially devoted to the Pac-Man game. So I think that people will ask you some questions about how to solve Pac-Man with the options framework. So just anybody who can ask a question, just go here and ask Doina.
Hello, Doina.
Hello.
Thank you for your talk. I would like to ask about how do you choose number of options. I saw you have sometimes 4 options, sometimes 8 options, and why not, for example, 100 of options? How do you choose?
Yeah, that's a very good question. So generally, we don't want to have too many options because the more options you have, the more parameters you have. And so, if you have a very large number of parameters in your approximator, it will take more data to train. So we have generally tried to limit the number of options. And so, we've tried very often in these tasks with something like 2, 4, 8, and not much beyond that. The other thing I will say is that as you increase the number of options, there is a redundancy that develops between the different options because our objective does not include any penalties for options essentially converging onto very similar policies. And so if you go, for example, to something like, let's say, 16 options, the performance of the system may end up being roughly similar, but if you look at what the options are doing, you'll see that are very correlated with each other. And so the marginal benefit of having more decreases. We don't have right now any theoretical justification for how to choose the number of options. It would be very nice to have that. But right now, it's basically done by experimentation and trying things out. And I think it also depends on the complexity of the domain at hand. So a lot of the tasks that we've looked at, these Atari games, are fairly simple. So something like 4 options is okay. But I could imagine that if you had more complicated problems, maybe strategy games or something like this, that larger numbers might be useful.
Any other questions? Hello. For the lecture, you have said that the options with the training are dissolved into simpler actions. Could you say some more words about this? Because I don't understand exactly why it is happening.
Yeah, so basically, when we think of a Markov decision process, if we really have an environment that is a Markov decision process, there is a deterministic optimal policy which is defined in terms of primitive actions. And so this is a result that's been established by Bellman back in the 50s. It's a classical result. So we know that the best reward possible can be achieved with just primitive actions. Now, our objective when we optimize is simply the total discounted reward. And so from the point of view of the subjective, using options is really not necessary. The options might give you a sort of temporary boost of speed, but eventually you would want to go back to primitive actions to get sort of the best possible policy. And so if the system is left to its own devices, if it had a tabular representation, it would pretty much always go back to primitive actions. When you have function approximation, there may be an advantage to keeping temporal extended actions, because function approximation essentially introduces partial observability. And partial observability, if you imagine, for example, a robot going down a dark corridor, it might be good to just keep going in the same direction, right, in order to get out. And so with function approximation, it's not necessarily the case that everything will be shrunk down to one time step. But still, the trend is to essentially allow you to control the system at a faster time scale. And of course, if you're at the faster time scale, you can simply change your mind more often. So from that point of view, of course, you're going to achieve better rewards. Now, what we do in the Atari experiments in order to prevent this is essentially put in a regularizer that is very much similar in spirit to this deliberation cost. Basically, in order to switch from an option to another one, we require that the advantage is above a certain threshold. And this is a threshold that we pick for the experiments. And so the intuition is you don't always want to switch between options, only if the one that becomes available is actually much better, you want to switch. And one could play with this threshold by, for example, decreasing it over time. We don't really do that. We just pick it at the beginning. The algorithm is not very sensitive to this parameter, but this parameter needs to be non-zero in order for the options to not disappear in the long run.
Okay, thank you.
Okay. Doina, you have touched in your answer relation between options framework and partially observable markup decision processes. Can you elaborate a little bit on that? So how options can be applied for the partially observable environments? Because it seems natural that if you have many alternatives and you have no information about hidden variables, to choose one of them, so you can relate different options to different alternatives, and then you just switch between them when you have like your model predict you what alternative you should choose an option.
Yeah. So the theoretical framework of options is developed using Markov decision processes. In practice, most often we don't actually have an exact MDP property, and so options can work with partially observable Markov decision processes. And in fact, there's been some interesting work in the robotics community from Leslie Kelbling and others showing that temporal abstraction can actually help you sort of jump over areas of partial observability. So, as I was describing, if you're in an area where you have very imprecise state information, you would want to just execute some sort of current course of action until you get to a place where the Markov property more or less holds. And in that place, your value estimates will be more accurate. And so a choice that you would make among different options would also be more accurate. Now, there's actually, so there's a little bit of work that's been done in this area. For example, there is a little bit of work from Sorg and Singh looking at options that work with linear function approximation. Linear function approximation does introduce partial observability, for example, if you're doing state aggregation. And there is a way to write out models for that case and to do Bellman equations. And they have a paper. They had a paper in, roughly speaking, 2010, explaining how that would be done. But general POM-DPs have not been tackled very much, and it's actually an interesting problem. What's the right way of embedding options in that framework? Now, the other thing that I will say is that you might have many different options, but in a POM-DP, very often you would want to limit, as you were mentioning, the number of options that are under consideration at any given time step. And this is basically because if you are doing POM-DP planning, the planning algorithms are essentially based on search, and that search involves expanding values for all the available choices. So if you have many choices at every given belief state, that kind of explodes the complexity of the planning process. So one would need to be careful to not have too many options, and to also use them as much as possible in places where the belief state is more or less deterministic, so that the Markov property holds and the theory is not violated too much.
Okay, thank you. More questions? So I have one more question. It seems that Pac-Man game should be more effectively solved with sub-goals. And so I personally expect that if we use options, we should have better results than EQN, for example. But as you showed, especially for the Pac-Man game, it was just a little bit below EQN. What do you think about this? Why this didn't work out for this piece?
Yeah, so the Pac-Man game, we had results slightly below DQN, and it's true that in this case, intuitively, sub-goals should really help. I think part of the reason why the results are slightly below DQN is that you have the option-critic algorithm does not necessarily learn exact sub-goals. So, one experiment that we did not try, but would be interesting to try, is to actually specify sub-goals, exact sub-goals, and then give extra rewards for achieving them and learn options that way and see if those results are better. What I suspect is that Option-critic is learning a stochastic termination condition that takes into account not only where sort of human plausible sub-goals would be, but also other places. And this is the reason why, perhaps we're not observing a huge amount of improvement in this particular game. Now, the other thing that I will say is we may well improve, even in this case, if we looked at noised up versions of the game. So there's been some work now on basically taking Atari games and perturbing them in various ways in order to look at the ability of algorithms to do transfer learning, to transfer knowledge from task to task. I think in that case, actually, the options would have an advantage over DQN in terms of the speed with which they can actually adapt to the new conditions.
Okay, thank you. So, any more questions? No. So let's thank Doina for her great video.
You're very welcome. Thank you for having me.
So I will just show you our audience a little bit, because you have seen only the backs of the audience, unfortunately.
Very nice.
Yeah,
so everybody is spending this week programming Atari games?
Yes, yes.
Well, that will be fun. I'm curious, I'd appreciate a short email to let me know how the results turned out.
Yeah, we will write you an email with the finals of our hackathon.
Sounds great.
Yeah. Thank you.
Okay. Thank you very much. Bye-bye.
Bye-bye.